จะขึ้นหน้าจอให้ไหมคะโอเคนะคะ All right. All right. Very good morning to our distinguished guests, ladies and gentlemen, and I would like to greet our online participants. Thank you for joining us today, and I hope all is well. Before the presentation begins, let me tell you how this special talk will run. Firstly, our guest speaker will present the special talk for about 60 minutes. Following that, we will have a question and answer session for approximately 20 minutes. And finally, the session will be end by a conclusion. Before we start a special talk, first, I would like to read a brief introduction to our speaker, Dr. Koji Shimizu is an assistant professor in Department of Materials Engineering at the University of Tokyo in Japan. He joined the University of Tokyo after his PhD in the Department of Applied Physics at Osaka University. His current research is development and application of machine learning-based interatomic potentials to investigate various materials properties. Ladies and gentlemen, without further ado now, allow me to welcome Dr. Koji Shimizu to present the special talk on neural network potential study of complex solid system. Dr. Koji, please.
Okay, can you hear me? Okay, so thank you very much for the introduction. My name is Koji Shimizu from the University of Tokyo in Japan. And I'm visiting here as a part of the collaborative research project with Dr. Tongjai Chokajon. And I'm so glad that you are accommodating us for the visit. So I'm here with two of our students, Kentaro Miyamoto and Koki Otsuka, and we are in the group of Professor Watanabe in the University of Tokyo. So in our group, we have been working on the machine learning interatomic potentials, especially which are applied to the solid systems. So I'm happy to share some achievement today. So here is the outline of today's talk. So let me briefly explain the research background and the methodology about what is the neural network potential. And after that, I will talk about 4 applications if time allows. So, okay, and I'm focusing on the first part and also the last part. This is directly related to the project, EHA project. Should I use the pointer or is this later pointer you see? Okay. Okay, so sorry for the J. So, okay, so some of you may know or may familiar with the machine learning interatomic potentials already. But the machine learning potential have attracted much attention in data-driven material science in recent years. And I'm thinking this is because of the development of the machine learning techniques owing to the information technology communities. And also another reason is that we are currently able to generate a lot of data using the first principles calculations, like with using these kind of moderate sizes. So now we can let the machine to learn the relationship inside this many data set. And the machine learning potential can be applicable to the larger systems like this kind of scales. So we are expecting that the prediction accuracy of machine learning models is as close as the density functional theory. But the computational cost is much lower than the density functional theory calculations. So if we put the relationship between accuracy and the scale in terms of time and or space, which is in between the empirical potential calculations and density functional theory calculations. And we are trying to shift the machine learning potential right upper side by making the sophisticated by using the sophisticated method or algorithms. So, so as you may know that the various methods have been already developed. The representative ones are high dimensional neural network potential, which I called here after NNP, and also Gaussian approximation potential. And the development of these kind of methods are quite active, and there are many methods, and some of the recent works using the graph neural network based method, so-called like CNET or Allegro. And today's topic is mainly based on this NNP method, but our group have been also trying this state-of-the-art machine learning potential method, which we hope introducing in the future. So as I mentioned, we have been using neural network potential, and we have applied it to some various systems like gold and lithium alloy system, which if you attended the workshop last year, you may perhaps remember this kind of figures. And also we have doing some development by modifying the neural network potential scheme, and so that we can apply the method which was unable to use to investigate the system, like the charge defect in the gallium nitride. It's not limited to the gallium nitride, but the charge defect case have never been considered by using the machine learning potentials. If time allows, I will go in detail about this topic. So the point here is that the machine learning potential enabled us to investigate the complicated system accurately, but the computational cost is quite low comparing to the DFT calculations. So next, I will briefly introduce about the neural network potential. So this is the schematic of the neural network potential. So what we want to do is to find the relationship between structure and the energy, because this is force field. And in the neural network potential, what we do is to construct this relationship utilizing the neural network. So given a structure, what we give to the neural network is the structure information, like numerical information, which represent the local atomic environment. So for respective atoms within a specific cutoff radius, we count it, we look for the surrounding atoms, and we calculated the local environment using so-called symmetry functions, G. So the exact symmetry functions are like this. So we are typically using two body terms as well as three body terms. So in the two body terms, which are the summation of the Gaussian function, this Gaussian is depending on the distance between the central atom and the surrounding atoms. So summing up all these Gaussian function will give you one numerical values. And in the three body terms, in addition to the Gaussian part, we also have the angle part. So we can get different values by using these two and three body terms. And as you can see that in these functions, we have several parameters like eta, lambda, zeta, and these are indicating the decay factor or peak position of the functions. So we prepared different set of parameters, and we finally get a set of different numerical values, and which can be given into the neural network. And then we passing these values through the neural network, and output we consider as the energy of atom I. And if you are interested in the technical part, the atomic energy can be calculated like this when you consider the two hidden layers neural network potential, fully connected neural network. And the W are actually the parameters which is associated with the solid lines in the neural network. So we have a lot of parameters W inside the neural network. And then total energy of the system can be considered as the summation of atomic energy EI along the component atoms in the system. And then we can also calculate atomic forces by the derivative of total energy with respect to the atomic coordinate alpha. And technically speaking, which can be calculated analytically by considering the chain rule of energy and symmetry functions. I will not go in detail about this part, but we can get energy and forces through the neural network. So this is what we are doing in the neural network potential. And then the parameters, as I mentioned, which is in the solid lines in the neural network, is updated to well reproduce the density functional theory calculation data. So like we have a large number of different atomic configuration, and we know what are the energies in these atomic structures. So we update the parameters to fit these values with the DFT data. So this is we call this as the training process. So this is sorry, and I forgot to show this what the symmetry function looks like. So these are two-body terms. By changing the parameters, the Gaussian function can change the decay factor or shift peak positions. And also for the three-body term, we can change the shift angle, the peak angles, like in the 180 degree or 0 or 360 degrees. So we prepared a different set of parameters to where this represent the local atomic environment. So this is the brief overview of the neural network potential. And we apply this method firstly to the crystallization of Li3PS4 glass. So which is still not officially published, but you can access through the archive if you are interested in. So this Li3PS4 is one of the potential materials used in the lithium, all solid state lithium batteries. And it is known that when Li3PS4 takes the form of glass, the higher ionic conductivity of Li3PS4 get increased. So this high ionic conductivity is the promising properties for the solid electrolyte. And interestingly, experimentalists also find that when the glass Li3PS4 is partially crystallized by heat treatment, the ionic conductivity of partially crystallized Li3PS4 increased. So this is the graph that experimentalists presented. Like the vertical axis shows the conductivity, ionic conductivity, and the vertical axis at the right-hand side shows the crystallinity of the partially crystallized Li3PS4. So when by heating the materials, it increased, the crystallinity increased. Along with that, the ionic conductivity is increased at the beginning. But if when the crystallization further proceeded, the ionic conductivity decreased. So this peculiar phenomena was observed through the experiment. And they have performed the microscopy measurement, and they found some connected crystalline nucleus like this, and they deduced that the mechanism behind this increase is like a percolation mechanism, but which is not very established. And there are other possibility like the interface. This is the schematic of partially crystallized domain surrounded by the amorphous glass domain. So one possibility is that the interface between the crystalline and amorphous plays a role for the improving the conductivity, or crystalline part, precipitated crystalline is important, or amorphous glass region changes their properties to enhance the ionic conductivity. So the understanding for these atomic scale mechanisms are not sufficient. So from our simulation side, we would like to clarify what is happening, what is actually happening behind these materials. But the problem is the density functional theory calculations are too heavy when we like to deal with this kind of models. So we applied the neural network potential to these target materials. So what we need to do first is the training dataset preparation. So I will just briefly go through this slide, but we prepared a lot of different atomic configurations using ab initio molecular dynamics simulations. So we set different temperature from lower to quite higher, around 4,000 Kelvin, and we generated various different structures from the ones close to the crystalline and also quite distorted structures. And in addition to the pristine case or stoichiometric case, we also introduced some of the vacancy, like lithium vacancy or Li2S vacancy. And these are the number of structures that I used for making the neural network potential. But finally, we used around 40,000 structures. And the table at the left bottom shows the root mean square errors of the neural network potential, which are basically around 12 or 13 millielectron volt per atom for energy, and around 200 or 300 millielectron volt per angstrom for force. And these are the parity plot for energy and forces. And the black one are the training, and the red ones are the test data. So, well, if you are familiar with the machine learning potentials, these values are not very good. But as we can see, all the data points are located on the diagonal line. So which are indicating the training very well. So we proceed. We proceed to the molecular dynamics simulations using the constructed potential. But in the course of making these structures, we used some techniques proposed in this paper. Like the main point is we did a lot of molecular dynamics simulations, but using the principal component analysis based on symmetry functions, which are representing the local atomic environment, we extracted only the important data set. So like this is an example. So this is PCA plot, and we have many, one point correspond to one structure. So we have many data set, but as you can see, we have many data points located at the same point. So that can be eliminated from the data set. So after eliminating unnecessary dataset, we get the PCA plot like at right-hand side. So using this technique, we prepared a 40,000 dataset and trained the neural network potential. So this is molecular dynamics simulations. So the target is the GRASS LI3PS4. So we want to make GRASS structure first by using merit quench method. And the model that we use is 5,760 atoms per supercell, which is pretty difficult when we just purely using density function theory calculations. So these are the procedure what we do in the merit quench method. So first we use the crystalline Li3PS4 structure, and the graph in the middle shows the potential energy profile and the temperature profile as functions of molecular dynamics simulation time. So if you look at the blue lines, the temperature is raised around 1,500 Kelvin, and it maintained for a certain times to melt the materials. And after that, we quickly cool down the material to generate this kind of metastable structures. So we evaluated the pair distribution functions for the obtained distorted structures, I hope. And then we can see, I'm sorry that this graph is busy, but if you look at those black lines, we have no specific peaks after the 4 angstrom. So this is indicating that the obtained structure is GRASS. And there is a study doing ab initio molecular dynamics simulations, and they also presented the pair distribution functions. And when we compared the pair distribution functions, were agreeing with each other. So, which means that the neural network potential that we have is quite accurate, which can reproduce the data set calculated by the density functional theory level calculations. Then, so from that GRASS structures, then we need to do some heat treatment, again by the molecular dynamics simulations. So in this molecular dynamics simulations, we call it annealed at 600 Kelvin. And for the ensemble, we use NPT ensembles. Then here, this is the animation of the molecular dynamics simulations. So one frame corresponds to the 1 nanosecond. And if you look at the part at the bottom, you will see the crystallization from here. So it suddenly nucleation happens and it extends to the entire cells. So the animation looks difficult to find which part is crystallized. So we change the way to visualize the snapshot. So anyway, here is the energy profile during the molecular dynamics simulations. And as you can see that we have the energy sudden drop of the energy around 70 to 85 nanosecond. So which is indicating that some of the phase transition occurred at this time scale. And then these are the snapshot at 73 nanosecond to 83 nanosecond. And in this snapshot, we put the colors on atoms based on the degree of structure orders. So the blue part is ordered. So the surrounding PS4 unit are arranged in the same manner. And that part is disordered, means which are close to the GRASS original, or which are close to the GRASS structures. So as you can see around, it started actually around 73 nanosecond. We can see some of the white colored region, and it expand and growing as the time it proceeded. And from 79 to 81 nanosecond, the crystalline nucleus connected in the lateral directions. And afterward, it extends toward the lateral direction, not vertical directions. And at 83 nanosecond, it finally connected toward this direction as well. And at 85 nanosecond, the crystalline region is already extended to the entire part of the supercell. So now we would like to see what is the crystallinity of the obtained structures. Then we perform the X-ray diffraction simulations. So these are some of the cases. And 0 nanosecond means before the annealing. So it is the glass structures. And we seldomly see the peaks in the profiles. But after 80 or 85 nanosecond, some of the peaks are visible. And at 90 nanosecond, the profile are mostly close to the crystalline structures. Then this is the values, crystallinity values obtained by integrating this spectrum. And at the same time, the volume, the blue circles, the volume shrink up on the crystallizations. So at the beginning, the crystallinity is below 10%. So which is again showing that our structures are glass initially. And it going to approximately 50%. Oh, where the entire structure looks crystallized, but the crystallinity is saturated at 50% because we have some of the defect inside the structures which prevent the further increase of the crystallinity. That is the current understanding. And then if you look at the crystallized regions, the arrangement of PS4 unit is like this. So which is actually different from the initial crystalline structures. And this is known as the high temperature phase, which we call alpha phase. So by doing the heat treatment, what we obtained in the crystalline region is the high temperature phases. Then, sorry, I'll go back. So as we can see that we have structures or we have models with different crystallinity. So we can investigate the ionic behavior at different crystallinity. So that is this slide. So for each structures with different crystallinity, we performed additional molecular dynamics simulations to get the diffusion coefficient of lithium. So this graph is the case when we set the temperature as 400 Kelvin. And the right-hand side is the annealing time, which corresponds to the crystallinity. So if you go right, the crystallinity increase, which is actually colored by the blue. So blue point more crystallized, and the white point is close to the glass. So as you can see, the diffusion coefficient changes as increasing the crystallinity. And by the way, the solid lines shows the diffusion coefficient value for the initial crystalline, which is beta phase. And the dotted line are the glass phase. And the right-hand side is the case of 600 Kelvin MD simulations. And from these data, we can plot we can get the Arrhenius plot like this. So the diffusion coefficient as a function of inverse temperature. And from the gradient of these plot, we can get the activation barrier for the lithium migration inside the material. So the right x-axis is same as the previous one, the annealing time. So at 70 nanosecond, just like before the crystallization happened, the activation barrier is around 320 milli-electron volt, which is close to the beta phase, and it gradually decreases as increasing the crystallinity. And at 80 nanosecond, which cross with the glass phases, and it decreased further. And after 85 nanosecond, the activation barrier is saturated. So from these calculations, we can get through the crystallization of the glass, the activation barrier decreases, and which is actually close to the alpha phase, which is nearly 0.2 electron volt. So what we obtained is quite similar to the experimental observations. And now we want to know where is the lithium migration path when we have some part of crystallized regions. So to know that, we plot the heat map of lithium displacement during the MD simulations. So here we show the 4 cases, glass 70 nanosecond before the crystallization, and in the middle of crystallization, and almost the last part of the crystallization. And the heat map of lithium displacement are shown at the lower panels. And as you can see in the grass, the heat map are quite, I'd say, uniform. But when the annealing proceeded, the uniformity is decreased. And at 80 or 84 nanosecond, if you compare the upper and lower panels, we can see the red region, which is high fast lithium migration region, completely, almost completely matched with the crystalline region. So in these calculations, what we found is that the enhanced ionic conductivity is mainly because of the precipitated crystalline phases, which is alpha phase. And when the alpha phases are connected laterally or vertically, the new lithium migration path are formed, which further enhance the lithium migration. So if you look at the activation barrier, the degree of decrease in the activation barrier is enhanced when we have the connected crystalline regions. So which is also same with the experimentally proposed the mechanism, that is percolation mechanism. So through these calculations, we can reproduce the percolation mechanism when we heat it at the 600 Kelvin. So probably when we use different temperatures, the mechanism may be different, because the high temperature phases will be precipitated at this high temperature, but when the heat treatment is lower, like 400 or 500 Kelvin, that alpha phase may not be appeared, and different mechanism will be playing a role. But at this simulations, what we found is like this. And finally, this is the local lithium density, and we can see by doing the annealing heat treatment, the amorphous region changes, glass region changes from the initial glasses. And with this kind of non-uniformity prevent the lithium migrate from one side to another side, and which can be actually predicted by checking the vibrational density of state, which is proposed by these papers. So if you look at the central position of lithium vibration density of state, if you have higher frequency, means the lithium is hard to move. But if the central position lowered, means the lithium is surrounded by the shallow potential energy, means the amplitude of lithium displacement is larger, then lithium is probably easy to move to the neighboring site. So that's what we found in these calculations. And I will maybe quick. So the second topic is about the development of neural network method. And what we want to do is to investigate the ion migration under the electric field. So which is important in several devices or several materials processing. Like interesting experimental data is like this. So this is called flash sintering. And these are the ceramics. And ceramics is known as the hard plastic materials. So if you put strain, it easily deform. But under the electric field, you can easily change the shape, right, without plastic deformations. So in these devices or processing, what we are thinking important are the defect formation or migration of ions under the electric field. But atomic scale understanding are not sufficient at this moment. So we want to do further investigations. So there are many calculations considering there are a little calculations considering amorphous structures. Not many previous studies considering amorphous structures by ab initio molecular dynamics, or there are not many studies considering the electric field within the DFT calculations. So we want to extend our neural network potential for such calculations. Then if we try to investigate the ion migration under the electric field, first we need to consider external forces acting on each ions. So to get these external forces, we need the information of charges. So simple way is just to use the formal charges. Like for the oxygen, we can assign -2, and lithium, we can assign +1. But we are thinking that those charges should be variable and changes depending on the local atomic environment. So we are focusing on one of the physical quantity named the Born effective charges, which is defined as like this. So the first definition is the derivative of polarization with respect to the atomic coordinate. And equivalently, this quantity is defined as the derivative of atomic forces with respect to the electric field. So this one, we believe that the situation is closely matched with what we would like to do. So here is the calculation scheme proposed in this study. So for given structures, we first construct the neural network potential used as the force field. And we prepare another neural network model to predict Born effective charge. And we can multiply the uniform electric field times Born effective charge to get the external forces. And some of them are considered as total forces. And by from these total forces, we can do the dynamical calculations. The objectives of this study is first we develop this model and also verify the ion migration under the electric field using Li3PO4 as a benchmark material. And this is a bit technical, but we just want to achieve this kind of model with the minimal modification from the original neural network potential. So we focus on the similarity in the equation of atomic forces, also the Born effective charges. So these are also or derivative with respect to the atomic coordinate. So we just replaced the objective function from forces to the Brownian effective charges. So because of the simplicity, our method is so far restricted to the one direction of Brownian effective charge tensors. But by changing this, and also we modify a little bit the descriptors, we can predict, we have developed a model to predict the Brownian effective charge. So we prepare the training data set again with these different structures, and we train the model like this. So here's the parity plot of the Brownian effective charges. And left one is for lithium and phosphorus, and the right-hand side is for oxygen. So as you can see, the parity plot shows, say, the right color shows the diagonal component of the Brownian effective charges. And as I mentioned, the formal charge is not always the case. So depending on the atomic environment, oxygen charges changes around negative, almost -3 to what is that, -1. So considering the local environment may be important. So this is the error of our model, which is not very small, but this is acceptable size of errors. So we proceed to the molecular dynamics simulations. So this one is without electric field, but the model we consider is like this, the lithium vacancy model, and also lithium 2O vacancy model. And this graph shows the mean square displacement as a function of molecular dynamics time. So in the pristine case and the Li2O vacancy case, the lithium mean square displacement all flat. So we ignore these cases because these are not mobile, even not mobile. And in the case of lithium vacancies, the lithium mean square displacement gradually grows, suggesting that the lithium is hopping through the vacant site. So we then perform molecular dynamics with electric field. So this one is without electric field, same as the previous slide. And this one is the mean square displacement under the electric field, where this electric field size is quite large, but we chose this value to enhance the motion, or to investigate within the short time period comparing to the real time scale. So comparing these two, without electric field, the MSD reached around 4 angstroms squared at 300 picosecond, but it reached around 70 angstroms squared, which is the scale is 1 order higher than with or without electric field. And the right-hand GIF shows the lithium trajectories under the electric field. So electric field is applied in the vertical direction. And as you can see, the lithium is migrating along the electric field. And we can see the trajectory only in this region because we have initially lithium vacancies at around this position. So this result is quite reasonable. Then since we have higher mean square displacement, we want to confirm the lowering of the activation barrier. So we investigated through the nudged elastic band calculations. So these two passes and obtained potential energy profiles are like this. So black open squared are the potential profile without the electric field, and it decreased to the blue colors. So as you can see, we have a certain height of barriers, but it decreased under the electric field. And it reversed, in the reverse direction, it increased more comparing to the case without electric field. So this is also a reasonable result. And if you look at the lithium migration path, we cannot see the obvious differences with or without electric field. But if you see the forces acting on ions, which has non-negligible difference. So of course we have differences along the z direction, which is the electric field direction. But we have differences in x and also y directions. So we want to know the effect of these directions perpendicular to the electric field, which is actually coming from the off-diagonal component of the Brownian effective charges. Then here is another molecular dynamics simulations to see the effect of the off-diagonal component. So we artificially set these zx and zy as 0. Then what we obtain is the purple lines. So the black line is the original mean square displacement under the electric field. But by setting these values as 0, the mean square displacement drastically decreased, which is still higher than the case without the electric field. And if you look at the mean square displacement along x and y, it's where it's busy, but we can see the frequent vibration when we have all three components. Oh, sorry. So this is suggesting that these off-diagonal components give the external forces perpendicular to the electric field is also important for the lithium motion, which is partly because, as you remember, that the lithium migration path is not direct completely along the z directions, which is partly going right and going back to the left. So this off-diagonal component has great influence on the lithium motions. So that is the interesting point, I think. And finally, we apply the same potential to the amorphous structures. So in this case, we have no specific defects. So the number of atoms are the same as stoichiometric. And then this one, again, the mean square displacement without the electric field, and the graph at the middle is under the electric field. So as you can see, the mean square displacement drastically increased in the amorphous case. So the increment of this mean square displacement is much larger than the case of crystalline case. So this is also this is actually surprising results. And if you look at the trajectory lines, you can see the lithium is going upward along the electric field, but not limited to the specific regions, but from the entire region, the lithium is going toward the z directions. So this is because this kind of metastable structures are susceptible to the electric field. So this is the second topic. And I will quickly go to the third topic. So I think in this institution, not many people are working on the semiconductors, but in semiconductors, the defect is quite important. So as you can see, the electronic or mechanical and thermal properties of materials are affected by the presence of defects. So there are many studies already, like direct observation of defects, and these are from calculations. Using the density functional theory calculations, we are investigating different kind of point defects inside the material, and we can see the stability or the concentration of defect formation, concentration of defect in the material, depending on temperature or other chemical environments. And nowadays, the number of studies are increasing focusing on the thermal conductivities, which is basically quite heavy calculations, just using the density function theory calculations. So machine learning potential may effective for these calculations. So there are already some previous studies doing crystalline silicon or silicon with vacancy, also the gallium nitride calculations. But the point here is that, as I showed in the previous slide, that in the gallium nitride case, specifically in the gallium nitride case, the stable point defect changes depending on their Fermi level. Like when the Fermi level is close to the valence band, the most stable one is the +3 nitrogen vacancy, but it transit to the +1 nitrogen vacancy at some Fermi level. So this difference in the charge state cannot be considered by using the conventional machine learning potentials. So we introduced some of the modification so that we can handle these different multiple charge states. That's what we have done in this study. So again, these are the structure data set, and we consider the nitrogen vacancy with neutral +1, +2, +3 charge state. And these are the number of data set we have prepared. Then this is the training results. So please assume that these dotted lines are the conventional neural network potential. So we have symmetry functions as input, and we have neural network, and the output is the energy. And in fact, by using this, the training result becomes like this. So the many data points are deviated from the diagonal lines, which means the predictions are quite bad. But what we did is just to put one node. We call it as system node, system charge node. Then the training results are improved drastically, especially in the energy. And these are the errors, which are very small. And then we verify the performance of our neural network potential by getting the phonon dispersion with the presence of nitrogen vacancy with different charge state. So the upper panel shows the pristine phonon dispersions. The left one is obtained by density functional theory, and the graph in the middle are the result of neural network potential. So the comparisons are quite good. Well, these unfolded phonon dispersions are quite difficult to differentiate it. But if you look at the density of states, the differences, you can see that differences are quite minor. And in the +3 charge state, there are some deviations, but overall predictions are quite good. And so actually there is a softened phonon state in which is correspond to this kind of breeze vibrations. This position is the nitrogen vacancy, and the atoms surrounding the nitrogen vacancies are vibrating toward the vacancy positions. And this is for the case of +3 charge state. The distinctive feature is the flat band at the upper part of the band gap. And just for your reference, these are the vibration state of this flat band. And these predictions are quite good agreement in between two methods. And then next is to verify the prediction performance of energies through the vacancy formation energy. So these are the equations, and what we get is this graph. And the solid lines are the DFT, and NNP are indicated by the dotted lines. So for 4 different charge state, except for the +3 charge state, we are quite good predictions. And these are the errors are tabulated in this table. And by including the phonon contributions, we can also see the transition levels as a function of temperatures. Because we have difference in the +3 charge state, we cannot see the transition at the left-hand side, but basically the predictions are quite acceptable size. So we want to reduce the errors in appeared in the +3 charge state, and we have been thinking what was the reason. And what we found is the poor sampling, like the +3 charge state has a little different optimized structures compared to the other charge state. So that specific structures are not sampled in our training dataset. In addition, some of you may know that we need to correct the energies when we introduce the charge defect. So by doing the correction technique, we have confirmed depending on the charge state and the structures, the correction needs large variations. So by including such corrections, we retrain the neural network potential, and we've got the refined one. And the defect formation energies is get improved, as you can see in the graph. So in this study, we stop at this moment, at this stage, but by changing the sampling techniques, we are expecting that the prediction performance can be further improved. So I will move on to the last topic. So which is, this is related to the collaborative project. We are doing high entropy alloy studies. So as you may know that the high entropy alloys are consisting of 5 or more component elements at nearly equimolar ratios, and which was reported firstly in 2004. So this is relatively new materials. And in theory, this is, by the way, this is schematic of high entropy alloys. And in theory, we are thinking that these high entropy alloys are stabilized from the contributions of configurational entropy. In the ideal case, we can obtain the configuration entropy by the composition of the materials. And as indicated by the figure in the literatures, in the early stage of high entropy alloy researches, they are focusing on their superior mechanical properties. But when you look at the surface of high entropy alloys, we can clearly imagine that there are different atomic configurations, and which is also expecting that when the molecules comes to the surface, they may find some suitable surface site to proceed their reactions like adsorption, dissociation, or desorptions. So focusing on these points, some of the researchers already started the calculation, not calculations. Some of the researchers already started the researches focusing on the HEA as catalyst. Then the publication is getting increased since 2010s, around 5 or 6 years ago. And there also exist some experiments. They are fabricating they are trying to fabricate high entropy alloy nanoparticles, including many elements. So in these examples, they only use the element in the platinum group, like ruthenium to platinum, and they apply this nanoparticle to the oxidation of ethanol oxidation reactions. So the current density that they obtain is obviously superior to the conventional or other catalysts like palladium or platinum. So this is promising results, promising experimental data, but using such platinum group element are not practical. So we need to optimize their compositions, element and compositions. So to do that, we can imagine that we need to choose like 5 or more elements from the periodic table. And in addition to the choice of the element, we need to optimize their compositions, like the small a, b, c, d, e. And then these are some of the examples, but the examples can be listed infinitely. So you can imagine that the number of configurations, number of combinations of these high entropy alloys are too huge. So we need to optimize, although we need to optimize the element and combinations, but this cannot be done by just doing an experiment, or it is extremely hard. So we are thinking to utilize some of the simulation techniques, which can make the progress faster, probably, but still exhaustive search is impractical. So in addition to this huge number of combinations, we need to also consider the degree of freedom of atomic arrangement. So we cannot propose the material just by proposing the compositions, but we also need to think where each atoms are located. So the search space of high entropy alloys are much larger than by considering the compositions. Then in our collaborative project, we come up with the idea that to optimize within the practical time, we need to utilize atomic simulations as well as the materials informatics techniques. Then we set our objectives as the exploration of high entropy alloy catalyst consisting of elements abundant in Asia like copper, zinc, tin, something, and also showing the proposed catalyst having the platinum level performance for the reactions. Then, as I already introduced, we are doing machine learning potentials. We want to utilize this method for the explorations. And then to construct this machine learning method, we need a large number of data sets. And then we firstly think about utilizing other open source database like Open Catalyst Project. So this is actually only the choice. But if you look at the content of this project, the database, including various many molecules and alloy surfaces, and the number of data sets are quite huge, but the models are limited to the SLAB models. And also the number of elements are maximally 3 elements in their alloys. So we decided to start to make our own database, partly because the catalysts are considered as the nanoparticles in many cases. So SLAB is actually approximating the nanoparticles in the large limit, but we are thinking there are still differences in the SLAB and actual nanoparticle calculations. So we decided to use nanoparticles form. And also nanoparticles have edges and also corners, which may have distinct properties comparing to the flat surfaces. And then we want to introduce not only the specific 5 elements, but we also want to optimize from a larger number of elements. Then I already mentioned, but we started to make cluster model dataset. Yes, so we started to make database. So here is the overview of our training dataset. So our element, these 9 elements. So this is actually same as the combination started with the Philippine group, one of our collaborators. So from copper to gold, we are dealing with these 9 elements. And the models that we are thinking is this bulk model, FCC 2x2x2, and also these cluster models, approximating the nanoparticles. So the smaller one is, we called it 3 layers, including 19 atoms inside the clusters. And the larger one, we call it as 4 layers clusters and consisting of 44 atoms. And from these 9 elements, we put some of the number of elements in bulk model or clusters. So here is the summary of our dataset. So for the bulk model, we consider up to 5 elements, so which is already the high entropy alloys. And using the package so-called supercell to consider all the possible configurations. So from a combination of some of the number of elements, we put into the model, and we calculated density functional theory calculations, including structure relaxations for all the possible combinations. And for clusters, it is extremely difficult to consider all the possible configurations. So we have some restrictions, and we have calculated multiple configurations, including up to 4 elements for the 3 layers clusters, and up to 3 elements for the 4 layered clusters. And we perform DFT calculations. And the current progress will be introduced later from our student, but the computational flow, what we are doing is that like this. So first, we randomly set the compositions like this, as mentioned earlier, the combination of A, B, C, D, E, randomly from the 9 elements. And then we calculate, for example, in the case of stability, we do the free energy calculations by using the thermodynamic calculations. We choose this because we want to consider the configurational entropy precisely, not the ideal one. And then from the obtained free energy, we give the result to some of the optimization algorithm, like Bayesian optimization or evolution strategies, to propose what compositions we need to explore in the next step. And then we go back to the composition. We propose it to the composition, and we iterate these circles until we get the saturated. Like in the case of stability, we want to minimize the system to be stabilized. And in the case of reactivity, we can maximize the reactivity to get the best composition with specific configurations. Then this is some of the preliminary results of our optimizations. So left one is the minimization of free energies, considering up to 9 elements in the 4-layer clusters. And the free energy is decreasing as the number of such increasing. And finally, at this moment, we got this is probably the most stable one. And we also make the prediction models for hydrogen absorption energy in this case. Then from hydrogen absorption energy, we can evaluate the activity of hydrogen evolution reactions. So we maximize this activity using these clusters through the Bayesian optimization. Then we got iridium, rhodium, core shell alloys have the best activities. So now we are already ready for predicting this stability or activities, and we can now combine the objective functions for the material to satisfy both stable and active at the same time. Then we can propose what is the best material in the near future. So this is the end. Thank you very much for your kind attention.
All right, thank you very much, Dr. Koji. Now, if anyone has any question, I'm sure that Dr. Koji will be very happy to answer them. And for online participants, you can leave your question on the chat box or use the raise hand feature if you have any question. Are there any question from the floor now?
I can ask a question. So thank you very much for the very nice talk. Very interesting and very fun. I was having fun when you introduced the electric field induced behavior of the ceramic material. So that was nice. I saw your update on the high entropy alloy catalyst. And then I noticed that the system that you're interested in right now has 7 components. Is that right? Yeah, the one in the lower left corner.
Mm-hmm.
7?
Yeah, 7. Yes.
I was just wondering with the size of the system.
Yes. This system size.
Oh, this system size. Yeah. How many? What is the maximum number of elements that could be that could be accommodated in this particle?
In this particle, you mean?
Or the ones that you tried? Yeah.
Based on the stability.
Yeah.
Based on the stability, we haven't. The maximum size is limited to the 9 element that we is this 9 element because we have only these training data set.
I see.
But if we can extend this size, we have more training data set with including more element, optimization can be extended further. If the predicted one is actually stable.
I see. Thank you so much. And then on the right-hand side, the sphere with the white color, is that the hydrogen or what kind of?
Exactly.
Oh, yes. Cool.
So yes. So what is doing in this optimization is check all the symmetry site and to see what are the activation and what are the absorption energy on each site, and we get the average or we get the statistic in these clusters to see what is the actual activities.
Okay, thank you so much.
Thank you very much. Oh, sorry.
All right, any more questions?
Hello. So thank you for your talk. It's very interesting talk. I really like the second part, the electric field with the ceramic. Just curious that when the electric field introduced to the system, the some atom move, right? Move.
Yes.
Is there any calculation to calculate the thermal properties of that electric field induced?
Thermal property.
Yeah, like the temperature of the system increased drastically or not? It's just curious.
So within these investigations, we actually limited the temperature as 800 Kelvin, and as the beginning we are doing the higher temperatures, but afterward we set just these temperatures because like when we consider the application like these memory devices, the temperature will not increase at high temperatures. So it is not reasonable when we set the temperature like 1000 or 2000 Kelvin. So we want to maximally limit the temperatures as acceptable ranges. But if I say like this, I should choose much lower temperature like room temperature, but then the ion migration is not that frequent, so we cannot see what is happening actually. So to enhance their motions, we need to at least increase the temperature around 800 or something like that. Did I answer your question? Thank you.
Any more questions? I think there's no more question now, Professor. And finally, ladies and gentlemen, I would like to thank the speaker, Dr. Koji Shimizu, for the informative and interesting presentation, and also all the online and on-site participants for your active participation. Please give a big round of applause for the speakers and for you all. And so see you later, and thank you very much.
Thank you very much.
ขอบคุณค่ะ